Hello everyone, and welcome back to my channel. This video is all about kinetic molecular theory of the gases. There's going to be a quick introduction, and then we can talk about the distributions of molecular speed. Okay. Okay, so we have already talked about ideal gas law, and we know that this law is going to always tell us what is going to happen to our gases if we are changing our pressure, volume, or even our temperature. But it's not going to tell us why exactly these things happens, right? To understand the why, we need to use our kinetic molecular theory of the gases, which has been developed many years ago. Okay, so let's take a look at the postulate or the assumptions that we have for this theory on the next slide. Okay, so the first and the most important one is that we have random motions for our gas particles. All of our gas molecules are going to be in constant but random motion. This means that for both the molecular gases like oxygen gas, nitrogen gas, or even for the atomic gases like helium, we're going to have random motions, right, in random directions. Okay. Now, the size of these particles are going to be very tiny so that we can say they have negligible molecular volume. The volume of the gas molecules themselves are going to be pretty tiny when you compare them to the volume of the entire container. We also need to always consider absolutely no intermolecular interactions between our particles. The gas molecules are not going to have any attractions or repulsion between themselves. It's going to be pretty much negligible. And also, we need to say that we have constant average kinetic energy as long as your temperature is constant. So they're going to be collisions that are always transferring the energy between the molecules, but the average kinetic energy is going to stay the same as long as our temperature is constant. And finally, the average kinetic energy is going to be proportional to our temperature, right? So if you have higher temperature, we're going to have faster movements for our molecules and gases, and all of these gases are still going to have the average kinetic energy that is staying the same, right? So as long as your temperature is the same, the average kinetic energy is going to stay the same. Now we can connect our theory to our gas properties. The first property is pressure, which is caused by molecules colliding with the container walls. So if I have more frequent or more forceful collisions, I'm going to have higher pressure, right? That makes sense. The second property is temperature, which is the measure of the average kinetic energy of gas molecules. If you double your absolute temperature, you actually double your average kinetic energy, which is exactly the reason that we have more molecular motion, right? We can also answer some of these really common questions. For example, why gas expands when heated at constant pressure? And the answer is we have our molecules that are moving faster, right? Because we increase the temperature, colliding with the walls more energetically. And as a result of that, the volume is going to increase to keep the pressure constant. The other very good question is why pressure increases when the gas is compressed at constant temperature. And the answer is molecules are going to collide more frequently with the walls, right? Because there's less space between them, which is causing the temperature to increase, right? I hope that makes sense. Okay, so as you can tell, the molecular speed is something that is a pretty, hot topic and the focus for this theory. So let's talk about the distribution of molecular speed. Okay, so our molecules are going to move at different speed, even though a gas has the average kinetic energy and therefore an average speed, individual molecules are going to move at different speeds. Our molecules are going to collide frequently. The momentum is going to conserve in each collision, but after collisions, one molecule might speed up, the other one might slow down, right? So as a result, you can say at any moment, the gas molecules are going to have a wide range of speeds, okay? Okay, so one of the very important property of the gases that are affecting our molecular speed is actually our temperature. So generally speaking, the higher the temperature is, the more molecules are going to move faster on the average, right? So look at this example here. I have nitrogen gas at 0 degrees Celsius and 100 degrees Celsius. When you increase your temperature, when you get to 100 degrees Celsius, we're going to have more molecules that are having higher speed, right? As you can see here, the red curve, it's kind of broader. So we have like more of the molecules that are having higher speed. Also, the average kinetic energy is higher at higher temperatures. If you look at our speed here, this is the average, which is higher than what we have for the blue curve, right? Okay. Okay, in the discussion about kinetic of the molecular theory, right, there are three common types of speeds that we can talk about for the gases. The first one is the most probable speed, which is UMP, and that is the speed at which most molecules are moving. If you look at the figure that I have here, the example that I have for you here, for 0 degrees Celsius, it's going to be like if you look at the height of this peak, that would be for like 4 by 10 to 2 meter per second. And if you look at the 100 degrees Celsius, that would be 5 by 10 to 2, right? And you can see here, this will be the speed exhibited by the largest number of our molecules. Okay, that is the UMP. The second one is the average or the mean speed, which is the average of all the molecules' speeds. And that is slightly lower than the RMS. And if you look at what I have for you on this picture, right, for the 0 degrees Celsius, it's going to be like 4.5 by 10 to 2. For the one that has the higher temperature, it's going to be higher, right? The last one is the root mean square speed, the RMS, which is the speed of a molecule whose kinetic energy equals to the average kinetic energy of all the molecules. Okay. And in terms of the value, the URMS is slightly higher than the average. For example, if you look at the 0 degrees Celsius, right, the blue curve, it's going to be less than 5 by 10 to 2, right? And for the one that is like 100 degree, it's going to be about 6 by 10 to 2 meter per second. Okay, cool, cool. And the last thing is about the effect of temperature on the speed distribution. As you saw for the 0 degree and 100 degrees Celsius, when we increase the temperature, the distribution's curve is always going to broaden. This means that the average of molecular speeds are going to increase, right? Okay, cool, cool. Thank you very much for watching this video. I hope you like it. There are going to be a couple of more lectures for this chapter that are coming up soon. Until then, take care. Bye-bye.